Very good afternoon, dear participants. Resource person for this technical session, Honorable respected Dr. Pramod Watekar sir is with us to discuss about introduction to optical fiber manufacturing, that to of commercial fiber manufacturing, the things which happens at Sterlite Optical Technologies Limited, Aurangabad.
Right.
I request my colleague, Professor Maruti Kumar sir, to introduce today's resource person for this session, Pramod Watekar sir. Kumar sir, please.
Yes, thank you, sir. Hello, everyone, and welcome to today's session. It's a great pleasure for me to introduce our speaker. He is going to talk to us about advancements in optical fiber sensors. Dr. Pramod Watekar. Dr. Pramod Watekar is currently working as a chief manager and research and development in Sterlite Technologies Limited, Aurangabad. He is associated with design and development of optical fibers, optical fiber cables, fiber sensors, and recently with process of optimization. He was an Indo-French IFC-PR fellow, then Department of Atomic Energy fellow, Brian Korea fellow, and then Brian Poole Korea fellow. He obtained his PhD from Indian Institute of Technology, Kharagpur in 2004. After that, till 2010, he was a research professor at GIST, Gwangju, South Korea. He also holds executive MBA from Indian Institute of Management, Bangalore. Please welcome, ladies and gentlemen, to our speaker, Dr. Pramod Watekar, sir.
Yeah.
Welcome, sir.
Yeah, thank you, sir. Yeah, thank you very much for beautiful introduction. All right,
Share
yeah, I will share it right now.
Yes, no problem.
Okay, thank you, professors, for that beautiful introduction, and welcome to everybody. Yeah, for attending this talk. It's my pleasure to give this talk to you. Sorry. Before actually we start our discussion, I will just briefly introduce Sterlite Technologies Limited, because that is what we are do, in any talk before starting our lectures. So our motto is actually transforming everyday living by delivering smarter networks. So we are no more only fiber optic manufacturer. We actually nowadays give smarter networks. Okay. Just I have to take one important call from boss. So मी नंतर काय करतो तो टॉक चालू आहे तू चालू कर. Sorry for that. So why do we need to know this type of companies, or why do we actually work on optical fibers? Generally, when we use internets, and we need optical fibers for that, right? 4G, 5G is compulsorily optical fiber based network. And from the historical point of view, if there is increment of internet users by 2 times, that actually increases data consumption by 22 times. So huge actually change in data consumption. For example, there's some figures are there. In 2012, internet users were 2.4 billion all over the world, and projected use was 4.6. That was estimated. And data, which is 0.4 gigabyte per month, increases projected to be 8.9. I mean, this is 20 times. But in practice, it is the natural flow. But in practice, because of COVID situation, this data consumption was increased tremendously. Okay, that's artificial. This non-linear increment was there. Okay, so integers are increasing, so data rate, data requirement is increasing, and that's where we are jumping in. We are optical fiber manufacturers. Briefly, when we talk about optical fibers for communication, there are two things. We need to have high bandwidth, so that many and more connections can be given. At the same time, it is not just bandwidth; it is latency, means delay. How much delay it can give, right? So nowadays we are going for virtual reality, augmented reality. The games are there, right? People, kids play the games. That augmented reality. In that case, you need very low delay time. We want everything to be very immediate. For example, if you go for Google Map, small delay can change your square. You can just pass that choke or square and miss the road. So that latency, that delay is very important. So we are expecting less and less delay. Okay, so ultra low latency is the requirement, and that's why optical fiber manufacturers, fiber designs are evolving to accommodate that requirement. Okay, so we need higher bandwidth and low latency. That is the key now for new generations, for example, 5G. Okay, let's go further. In that way, if you say we need more data, right, from last few years, you can see the people who are using internet, mobile, everything is increasing. So you need more and more data, and more data can be supported only by more optical fibers. Because wireless cannot support that bandwidth. Only optical fiber can support. So in 5G, we are taking fiber to your societies. Up to society, there will be antennas. So till then, from that antenna, small antenna, it will be wireless to your mobiles. So 5G is like that. It essentially requires optical fiber. Okay, so we are here. Just keep regarding Sterlite Technologies Limited. We are very unique because we get our own silicon from our own factories, not in India. It is Vedanta in Africa. So we get our silicon minerals. And from that, we make our own glass preforms. We make optical fibers. Okay, silicon to optical fiber, everything is ours. We manufacture cables. We use our fibers, manufacture cables, and we also do now the networking and FTTH. We are also involved in software development, and recently we are in cloud business also. So things are expanding, right? So we are not just optical fiber company, but we are actually data company. And data needs, whatever data needs, that we're trying to provide to the customers. That is Sterlite uniqueness. We are everywhere in the world. We are manufacturing facilities in China, in India, Silvassa, Valuj. We are in Italy. We are in Brazil. So they're all manufacturing facilities there all over the world. Okay. Just introduction here, there is a BharatNet is going on, right? Connecting all Gram Panchayats in India with optical fiber. So Sterlite is, Sterlite is providing that type of connectivity to all India. Because of COVID, it is a little bit now slowed down, but it's again taking place. Yes. We are also participating smarter city infrastructures in Gandhinagar, Jaipur, and Kakinada. Here we are providing optical fiber-based smart networks. For some use cases here, we are with Indian Army. Sorry, where we are building infrastructure in Kashmir. We are with Navy. Coming again to some facilities, we are building. Reliance is actually Reliance Geo. They are deploying various networks. So optical fiber cables are deployed by Sterlite for Reliance Geo. We are also, there are some projects are going on with Navy and with, civil guys. Where Sterlite is producing, actually providing smart turnkey solutions. Yeah, we are going from 15 billion. I mean, this is a 2 years data. We are going now towards, plan is to go for 40 billion and then 50 billion dollar. We also have now innovation centers. We have 3 innovation centers. Main is where I'm working, Center of Excellence. We have software delivery centers in Gurgaon for networks. We have academy where we provide educational services for other companies. So there are various, portfolios there. There are few snapshots of our manufacturing facilities. This is in Silvassa, India, topmost. Next is Metallurgica Bresciana, Italy. So we have cable manufacturing plant in Italy. Aurangabad, where I'm sitting now, is our facility. In Brazil, also we make optical fiber cables, and in China, we have in Haimen we have that fiber plus cable facility. In Haimen, generally, what we do, we make glasses in India and send to Haimen. That way, to avoid monopoly caused by China. That things. So we have various manufacturing facilities. New facilities are coming in Saudi Arabia. Yet not finalized. I mean, it's going on. Maybe Saudi Arab countries. For to cater requirements for America, we are in Brazil. So Curitiba, Brazil. From Brazil plant, we cater American customers. And in European customers are taken care by Italian Metallurgica Bresciana, but major part is actually done by Aurangabad, India. Most of our manufactured fibers, which are going to Europe, are from Aurangabad. And Chinese, that plant takes care of Chinese requirements, as well as Mongolia and all that type of things, or Pakistan. So Pakistan fiber is it goes through Haimen, China. We don't provide from India itself. Okay, so that's what we have a lot of manufacturing facilities, and we are going to expand from 30 to 50 million fiber kilometer by 2019. It is delayed now. we are at 50 million. Facilities, everything is ready. We are opening up slowly, and yeah, and requirement already there. Okay, but it was all closed down. The ships, we cannot ship everything. That was the case before 6 months. Now, once we stop everything, all process, manufacturing process, it takes a long time to optimize all those parameters. So we're all struggling these days after little opening up to tune our manufacturing facilities, our machines. Now they are gearing up. So where we are in Amazon forest. We have in Iceland's extreme snow. We have deployed our cables, Himalayan range. Then we have Formula 1 racetrack. We are everywhere. We are there. A lot of things are there. Okay. So I will just skip a lot of things. Thank you for listening to this introduction to my company, Sterlite Technology. Now I'm working in research and innovation field. I was earlier working in process engineering. Regarding this today's talk, it is based on my experience. It is less on theoretical basis. It is mostly on whatever I have worked. I work on glasses, manufacturing glasses, then optical fiber using MCVD, then OVD. Currently, I'm using OVD. There are very less chance in using vapor axial deposition also. So most of the things what I will discuss with you will be experimental things. But for what I have done, I have manufactured optical fibers using those experimental things. So I will try to share my experience with you without doing much theoretical jargon, so that we can make this talk interesting. Yeah, coming to our now introduction to all optical fiber manufacturing. Thanks to Shau Vidyalaya, Rajeshri Shau Mahavidyalaya, the Autonomous Institution, which has given me a chance to give this talk. And yeah, welcome on board all participants. let's go deeper into optical fiber manufacturing. How to do that?
सर ते हाईड आहे ना, हाईड खाली येते बघा, त्याच्यावर क्लिक करा. कधी कधी कंटेंट कव्हर करायला लागले ते.
Okay, thanks. Sorry for that.
Yes, no.
Okay,
Yes.
so what we're going to discuss is what is optical fiber, because we are not actually assuming any previous knowledge from you. So I will briefly introduce optical fibers, how to get optical fibers from glasses, and then we'll jump to some methods of glasses, from glass, how to get fiber, then chemical vapor deposition, MCVD, OVD, VAD. There are many methods, solder method, molten glass, extrusion. After that, I did work on extrusion, but we are trying to do extrusion in Sterlite now. But I work on molten glass, sol gel, VAD, those sol gel type things. They're really nightmare for scientists. Okay, so there are many methods, and I'll also introduce you how to do cabling of optical fibers, because we cannot just sell optical fiber. You must cable it, otherwise people will destroy it very quickly. So all those manufacturing, the beauty in the manufacturing of optical fibers, I will share with you. Just the introduction, how we had history of optical fibers has evolved. Long back, John Tyndall actually demonstrated that yes, you can actually bend the optical fiber. Sorry, light. We can bend the light by using any medium. Okay? Optical fiber is just a medium. So he has demonstrated light is not always straight. You can bend it. Yes, that triggered much research interest after many hundred years. Maybe. Okay, in 1930s there was some papers published where the scientists actually thought that time that we can transmit images through the fiber. So idea is very simple. I was to club different fibers together, thousands of fibers, optical fiber together, and we can transmit the image. But this was not much advanced, because it's very difficult to do. Actually draw the fiber and then send images there, because the light we see in those days, right? Incandescent lamps. So it was very difficult to introduce those light into the fiber. So it was non-commercial thing. It was only research laboratories, so it didn't materialize much until 1960s. Lasers were invented, and yeah, now we can, once we have a laser, we can introduce that light directly to the optical fiber. So that took a lot of research, fine optical fibers, and people started to use optical fibers. In 1970s, they found, okay, if you can use optical fiber, it is useless, because it's good for from a few meters. You are going for kilometers and kilometers, you cannot use optical fibers with huge loss. ऐसे use करना है, इतना loss है तो. So actually to transmit some signal, you need to have huge power that time. So then research started, yeah, itna loss क्यों है, how to reduce that loss. Yeah, that triggered which material to use and how to do that. That type of research thinking was evolved that time. Going further, what is optical fiber? I think everybody, but just sake of continuity, I will explain what is optical fiber. It is a thin strand of pure glass. We have glass, we actually make a very thin circular strand out of it. That is optical fiber. But it is not just a simple glass, glass strand. It has a deep complex structure inside. Inside we have, as you can see here, inside that is called as core, which has higher index value. Refractive index is high here, surrounded by cladding. Refractive index is low there. Why we do that? To have total internal reflection, so that the light which is passing to the core, the central point, it should remain there. It should not go there. So we have that cladding things. And to protect it from environmental things, we have coating. It is plastic coating. That is simple optical fiber. Let's move further. Optical fiber, why we use it? That it can carry huge information. Right? If you neglect attenuation, you can. It has huge bandwidth, terabits of bandwidth, huge bandwidth. You cannot imagine with these wireless things. Okay, and its weight is very low. It is very light. But most interesting thing for progress of optical fiber was the immune to electromagnetic noise. So idea is that if we would have not used optical fiber for communication, it would have been definitely used for military application, right? Because it is immune to electromagnetic noise. There is very good example here. It's not just a little bit out of this topic. In Iran, we send the fiber, which is dispersion shifted fibers. Nowadays, people don't use dispersion shifted fiber because the dispersion is spreading of the pulse, can be managed by electronics. So, but Iran and military, where military is very powerful, those guys are using optical fibers. The reason is that it is electromagnetic immune. If you remember, some of you remember Saddam Hussein's that war, America versus Iraq, Saddam Hussein's war. America jammed all the electronic equipment there. Right? So he could not convey, he could not give orders where to attack all those things. So that was, they were handicapped, Iraq military, because of jamming of electromagnetic jamming. But if we are using optical fibers, what happens? You cannot jam it. It is immune to electromagnetic. So even though there is a war, even though there is a problem, still the communication line will be open. So because of this thought process, a lot of countries are now using optical fiber, which are obsolete actually, which are not used in the communication field, optical communication field, but still used by the army guys. Even our Indian army is now deploying those dispersion shifted fibers. The reason is simple. It is immune to electromagnetic noise, immune to, any interference, artificial interference by any country or enemy country or anybody. Okay, that is the interesting example. So Iran is the main market for us for dispersion shifted fibers. Now coming quickly to our material selection for optical fibers. We are going to manufacture optical fibers, so we must start with materials now. Okay, while manufacturing optical fibers, we need to select the materials which have potential three basic qualities. Its loss should be very low. Okay. If you are sending the light through that fiber, through that glass, if I am sending 1 watt, I should get 1 watt as the output. If I am sending 1 milliwatt, I should get 1 milliwatt as the output. So losses should be as much less as possible. That is the main criteria. Then refractive index control. We must be able to change or tune the refractive index, right? Because there are various applications. It's not just, we are not just sending light. We have to manage dispersion. We have to manage, bandwidth. We have to manage a lot of wavelengths or dense wavelength division, multiplexing. A lot of things are done, and that type of applications, different application needs different optical fibers with different characteristics. Okay. For example, if you go about single mode fibers, terrestrial communication from India to America, if you are going to deploy optical fiber or optical fiber cable, what we expect is that the attenuation should be as low as possible, so that we need very, our power budget or requirement is low, limited, so that we can save a lot of cost. That is the requirement. So we have to manufacture optical fiber with that type of refractive index profile. And if you're going for other application, for example, in fiber to the home, FTTH, in that case, what happens is that your fiber gets, can have many bends, sharp bends, as like electrical wires. Fiber cable can also get that type of sharp bends, and if there is sharp bend, there is a huge bending loss. So to avoid that bending loss, we need to have different refractive index structure. Okay? For example, we provide trench, low index region around the core, that type of structure. So it means that we need different refractive index profiles, refractive index shapes. So what does it mean? That material should allow that, right? If you are designing some fiber on the paper, but we should be able to manufacture it. So RI control is very important. Then shape control, right? Shape of the fiber. We should be able to control it because it should not be, elliptical or some different shape, weird shape. It should be perfectly circular. So we should be able to control the shape. So that material should be flexible. So optical loss should be low. A refractive index should be controllable, and shape should be controllable. That three properties are there. And based on these three, we should select the material. Let's try to select material now. We have gas. We have gases and liquid, right? Simple things. Gas, liquid, and solid. So let's start with gas. Gas is the best material in terms of attenuation. We get the similar light. So that's the best material for and then for low attenuation communication link. It's very good. And they're still used. Right? It's not that gas we don't use gas. We use gas. We still use gas. For example, we have CO2 laser. You want to pass CO2 laser. Then we have to use gases. Right? We use optical fiber only for the guidance. Inside it is a hollow fiber, and we can send CO2 laser through it. Photonic crystal fibers with hollow pores. So gases are still used, and that's very important. Gases we can use for sensors, right? So we'll see tomorrow how we can use the structures for sensing application. But gases are still used. It's not that it is obsolete. But problem is that advantage is it is low attenuation, low losses at generally higher wavelengths. But problem, as I explained you, very fatal problem is that we cannot control refractive index. Right? In gas, how can we control it? It's very random moment. So we cannot control refractive index. So we cannot make very complex structures. Whatever we need in optical fibers, we need different refractive index structures. So it's very difficult with gas. But yeah, gases are still used in optical fibers. In a sensing application mainly. They're not obsolete. So we use it. And then there is liquid. You will say, okay, what we do there generally, we add some liquid material. We take the glass rod, make central, there is hollow region in the center, and insert the liquid. That's simple, so simple. You draw the fiber. It is still done. Now we will say, okay, similar problem here also. Refractive index change in the liquid. Temperature changes, the refractive index will change, and your property will change. So liquid is not much preferred, but it is still used in sensing evolution. Who uses liquid? I have seen cat indoor, right? That Center for Advanced Technology cat indoor. They have optical fiber center. So we used to. I was there during my PhD for some projects. So, those guys were using liquid field optical fibers for some sensing application for atomic atomic equipments. So liquid field fibers are still used. Okay, it's not that they're obsolete, but they are used for very limited use. That is sensing application. Gases and liquid, they are used for sensing application, not for optical communication application. The simple reason is that the refractive index control, that's very important. It's very constant. That's not possible. And then, yeah, we have exhausted our gas and liquid. Both cannot be used for optical communication. It can be used for sensing application. Then we have a solid. Let's use solid things. Okay, so if then people started, okay, we have silicon crystals, Si crystals. So why not use crystalline structure for optical fibers? I mean, for optical communication, not fiber, I mean optical communication. So yeah, actually, we have crystalline and we have two materials, right? Crystalline is where molecules are nicely arranged. That is crystal. Where they are loosely arranged. That forms the amorphous material. So crystals actually are very, very good for losses. Okay, they are huge. I mean, so ultra low loss, 0.1 decibel per kilometer, very low. Just for your reference, we generally look for 0.2 decibel, right? 0.18, 0.19 decibel per kilometer. We say, okay, very good fiber. But if you use crystal, okay, for optical communication, you get only 0.1. So, right, nearly 50% advantage there. So crystals are very good, but it's very difficult to mass produce. We need kilometers of fiber, right? We have to go from India to America, European countries. We need to communicate on that scale. We cannot manufacture a crystal of that at that scale. It's very difficult. Second thing is we cannot draw fiber with crystals. So crystals are not they are not using optical fiber communication. We don't make it. And then people said, okay, if crystals are so difficult, it takes a long time to manufacture. So we can use polycrystals, right? Polycrystalline structure. But soon this idea was dropped because it showed huge attenuation. Huge absorption was there because of scattering. So if you send some power and output power was very low. So crystals, don't use, okay, gone. Then, okay, we have exhausted crystals, gas, liquid, crystals gone. We are left with amorphous material now. Okay. So amorphous material means glasses. We found that they are the best suitable material for communication. Okay. And there are many materials now. Glasses means not just silica. There are many materials. Silica glass. We have chalcogenide glass. Chalcogenide means this sulfides, selenite, tellurides. These are called as chalcogenide glasses. And fluoride gas glasses. So many glasses types: so silica, chalco, and fluoride. I'll talk about chalco here. Chalco, very good material if you are going for low attenuation. This is very low attenuation than silica. But problem is that they are poisons. It's very difficult, right? To handle poisons material. Nobody will put here. Jaan khatar mein kaun dalega. So chalco are very good material. They are used in sensing applications, but not for optical mass optical communication because of difficulty in handling. So we also don't use chalco. Chalco materials are generally used in laboratories. Okay, once one memory when I was in Gwangju, South Korea, GIST, Gwangju Institute of Science and Technology. The professor brought he was a glass scientist. He bought that chalco materials, and we were scared. Oh, who will touch that? So that's there, right? Jaan pe khatra hai. Chalco glasses. So I never work on this type of things, and they are not popular also. Next is fluoride glasses. They are the fluoride glasses are very useful. Okay, even though they are not used in mass scale because of difficulty in doping fluorine in the fiber, but they are still used for some special structures. For example, bend insensitive optic fibers. We need to have that fluoride glasses. Then coming to silica, that is it has won the race among all the types of glasses. Silica glass is the winner because we can easily draw fiber through it. It has low scattering losses. It is not poisonous. So that makes silica very suitable material for optical fibers. Okay, so silica is the very popular material nowadays. We move further. It's very easy to get SiO2, right? It's from sand. Sand is SiO2. Only then work for us is to clean it. So SiO2 is in abundance available. We can control different index. We can control its shapes. Whatever we need, right? We need to control different index, shape. So everything possible. All things are possible here. So SiO2 is generally use SiO2 there. And another material that glass material that we use along with SiO2 is germanium dioxide. Okay. Earlier we used to have titanium, TiO2 as a fiber core, but TiO2 is very popular in integrated optics. It's very popular material. But in optical fibers, if you take optical fibers for communication, TiO2 is not used. But the thing was that we get attenuation of the large there. 17 to 20, right? We are talking about 0.2 decibel per kilometer attenuation, and here it is giving 70 to 20 decibel attenuation per kilometer. So it is huge attenuation there, TiO2. But titanium, it has very high advantages in quantum dots or titanium quantum dots, something like that. There are specialty applications there. Okay, but in commercial things, we don't use titanium. We use germanium because germanium is like silica. We can control its concentration. Uh, Germanium glasses, we can control the shape. We can control the Faraday index. So we can draw the fiber nicely. So GO2, SiO2, that combination has become hugely popular in optical fiber communication. Okay, so we understood that we have now glasses, that is SiO2 and GO2. These are the two main materials because of their usability in manufacturing, mass production. Okay, so we use GO2 as SiO2 instead of crystalline gases and liquids. Now, if you want to use SiO2 now, then we need SiCl4, right? We need GeCl4. Just we'll introduce quickly. But I'm taking SiCl4 because we have we make SiO2 here, right? So we have our plant here. So what we do is that it is very simple. We have silica metals, heat it, थोड़ा गर्म कर देते हैं, hit the silica metals, pass chlorine over that, and you're gonna get SiCl4. It is so simple. It is chemically it is so simple, but practically that impurities that are spoils there. But okay, impurities are everywhere, right? We have to clean it, and we have to do many various steps to attain the purity, 99% purity. But in simple terms, you take silica metals, heat it, 80 degrees, something like that, not much temperature, and then pass chlorine through it, and you get SiCl4. It is so simple things. And we also think we have to take care of moisture content. So why it is there, we'll discuss in coming slides. And to check whether our SiCl4 is good or not, we generally use FTIR spectroscopy and atomic absorption spectroscopy. These are the equipment there for ascertaining the purity of our SiCl4. So we manufacture our own SiCl4 here. It's simple, Si plus Cl, that is SiCl. And yeah, what are the losses? Just for your introduction. If there is two ppb, sorry, if you have 2 parts per billion, only 2 parts per billion, okay, billion atoms, 2 atoms, chromium. In that case, it will get 1 decibel per kilometer attenuation. So how much we want? Customers want 0.18, 0.19 decibel per kilometer. But though atoms are going, 1 billion atoms में chromium case, it can increase the attenuation to 1 decibel per kilometer. Huge loss. Okay. So chromium, Mn, ferrous, this cobalt, nickel, copper, they're all metals, transition metals, gives huge losses there. So we have to get rid of all these metals. So that is the complex process. Okay. So, that's why sometimes very difficult and very expensive. That removing PPB type removal of impurities is huge. It's cost. It costs a lot, billions of dollars. So generally, what we do, just we took business approach. In core, for the core part, we purchase pure SiCl. Okay. Aldrich or the different sigma Aldrich. So they have huge facilities everywhere. So for core part, we don't need much SiCl4. So we purchase that. And for cladding part, which is the actually 99% part, we manufacture it. We use our own SiCl4. If little bit attenuation there, I mean little bit impurities there, it is not going to affect the performance of fibers. So it's everywhere, right? All companies do that way. So very pure, 99.9999, that type of purity is used for core, and then for other things, it's okay. The reason is that even a small few ppb can increase the attenuation, and it can make your fiber fail. Okay, let's move further down. So we are coming to now glass manufacturing methods. We have studied which material to select. We also have studied how to manufacture SiSiL4. I'm not taking how to manufacture GSL4 things because we don't manufacture. So we manufacture SiSiL4. That is what major contribution there. So I have taken SiSiL4 there. I have not posted any picture the photo, but I was prohibited from posting photo to you. So I have not provided any photo, but yeah, I try to give small flow how we purify the SiSiL4. Okay, coming now to glass manufacturing method. It's very interesting things here, and I hope that there are no questions until now. If there are, you can ask. Okay, just stop me and ask me. Okay, so we'll move to glass manufacturing methods. Now, while going for glasses, we have various methods: sol gel, molten glass, double crucible, rod in cylinder, chemical vapor deposition. So these are the 5 major manufacturing methods. Okay, regarding sol gel method, I have one memory. What happens when I was doing my postdoctoral in South Korea? They had MCD, they are manufacturing optical fiber manufacturing facility, MCVD method. Those guys were not allowing me to touch their machine at the time, okay, because I was new, and they thought I don't have any practical experience. They were true also. In that sense, I had no experience in automated manufacturing. In IIT, what we used to do, we had MCD system. There were mass flow meters and everything. We used to go inside. It was not lot of time it used to malfunction, so we used to repair it. There's a big machine, right? To go inside, repair it. Okay, now working fine. We used to measure. Okay, yeah, flow itna diya, itna aa raha hai, theek hai yaar. Okay, so like that. हम पहले set कर देते थे, and then we used to manufacture that way. That type of manual operations, we used to do manual operations. In Korea, it was all automated. So really, I didn't know. I just joined. And it was cooling off period. And then we said what to do. Then that was time when I learned a soldier method, because there were used methods. I discussed with professor. He told while you are trained with this machine, this automated machine, you can make soldier glasses. So that is the history with soldier, is how I learned it. And there was some previous experience in IIT also. There is one group which makes soldier glasses. So problem with soldier is that there are huge cracks. You cannot make it. I mean, people make it, but it's very difficult to make that glasses without cracks. But still, you can publish papers because this is glass, right? And you can put a lot of things there and dope and study a lot. So I got initial papers on Sol-Gel publications, very new publications. But yeah, if you are going for mass manufacture, Sol-Gel is very slow process. Overnight रखना है, then keep it for overnight. You took TOS, add different things there, and then put it for at 60 degrees. Then you have to control the temperature, humidity, so as to reduce cracks. So Sol-Gel method is, it is a room temperature method. It is very good method, but its yield is very low. If you make maybe 10% something. So commercially, Sol-Gel glasses have not gained much attention. So some companies make it, but its yield is so low that not mainstream companies, they don't make Sol-Gel glasses. Except for specialized glasses, those companies who make specialized glasses, something like rare dome glasses or something. That type of companies, they use Sol-Gel method, but commercial manufacturing, Sol-Gel method is not much popular. Yeah, okay. Another thing is molten glass method. It's so simple. You take a glass, material, glass, whatever basic material required for glass to manufacture glass. Take those powders, heat it, it becomes molten things. Yeah, pour it there. You get the glass, not bangle guys or tube guys. they use molten glasses. So we can use molten glasses to manufacture optical fibers or preforms. But problem with the molten glass is that we have to lift it out of furnace and then put here. So a lot of manual things are associated with it, and there is a huge chance of it, adding impurity. Even your sneeze can add a lot of impurity there. And so molten glasses attenuation is always very high. Okay, unless you are going for short, a few meter or few centimeter type of glasses, glass application, fiber application. The molten glass gives huge attenuation, so we cannot use for optical convention. But yeah, there were some attempts by Australian group, right? Victoria University. Those guys tried to use molten glasses to make and manufacturing, and they were to manufacture optical fibers, and they were successful also. Yeah, but it is not much popular because molten glass means manual. You can automate it. You can make it robotic. Whatever you do, once it is in the environment, out in the environment, that liquid material, impurities can be added there. So there's a huge chance of getting attenuation. Then next is double crucible Rodin cylinder. I will just explain them briefly. Double crucible, it is very simple thing here. You have two crucibles. This is inside one crucible, outside crucible. You put core material here, molten glass here. You take another clad material, SiO2. Take SiO2, heat it. It is molten. Pour it here. This pink color. You take germanium plus SiO2 and heat it. It's got molten. Add it here, and then you pull the fiber. So that's the double crucible method. Yeah, people use it for multi-mode fibers. That type of thing. Some companies use that. Generally, research laboratories use this type of method, double crucible method. But they are not much commercially popular because of difficulty, to melt, right? गरम करना है इसको, melt करना है glasses को. You are pouring it, so there is a huge nightmare there. Playing with liquid. Another method is rod in tube method. This is very popular now. This is hugely popular method, rod in tube method. First is chemical deposition. That's number one. Another is rod in tube method. So this is we also use this rod in tube method for specialty fibers. It's very simple. You take core rod, right? Already this is a solid. It's not liquid now. Take a solid core rod there. Take a hollow another glass glass tube, silica glass tube. Isko core rod, insert this core rod into this glass tube. Yeah, so we have core, we have surrounding that core, we have cladding. So core, clad, everything is available. Heat it, melt it. Right? If you heat it, it will melt, and fiber will be drawn. Fiber will come out. That droplet from here. You heat it here, and you can draw the fiber here and pull the fiber. I mean, so it is a very simple method. Rod in tube method. We also call it in Sterlite, also in Germany, we call it RIC, rod in cylinder. Same, right? Rod in tube or rod in cylinder. We say RIC method. This method is generally used in manufacturing bend insensitive optical fibers. Okay, because in bend insensitive optical fibers, what we do is that we have core, and core is surrounded by fluorine dope region, some fluoride dope region. So, and to do that experiment is very difficult. So what we do, you take the core rod. Okay, we manufacture core rod in our factory. We purchase the fluorine dope glasses, the tubes. So उसके ऊपर रख दो fluorine tube, surrounded by another cladding tube manufactured by Sterlite itself. We can do it here. So we take all things and we can draw the fiber. So for specialty applications, this rod in tube is always preferred. So what are the observations that I will share with you when we make RIC rod in cylinder method? Before that, we tried with with our own system to dope fluorine in the optical fiber. So we were successful. to do fluorine in the glasses. It's quite possible. It's not, I mean, that's not rocket science. Only problem is, to maintain that structure, I mean, some profile shape is needed there because of heat. Okay. This fluorine, it can diffuse out. So we may not get the depth, I mean, refractive index value of what we want. So practically, it can be a little bit different than that. So adjusting our properties becoming very difficult that way. So what we did, okay, so this problem here. So we can directly purchase, then we can directly take this fluorine tubes. So we have now core rod surrounded by fluorine tube and surrounded by cladding tube. So 3 regions, and that way we can make the optic fiber. It is a bend sensitive optical fiber. We are still using this method. It is hugely popular. A lot of companies are using this method, Merrick method. Yeah. Then coming to most popular thing, that is the chemical vapor deposition. Yeah, before coming to this, I want to comment on this rod in tube or rod in cylinder method. Theoretically, it is possible to make any shape, steps using this rod in tube method. You go on and changing this cylinder, right? You take the core rod and go on changing the material for, you can go on adding different tubes of different sizes. So you can make many shapes, different shapes there. Okay, so that is the beauty of this rod in tube method. You can manufacture very complex structure using this type of rod in tube method. Coming to chemical vapor deposition. Okay. Because rod in cylinder is very good, it's very simple, but it's expensive. And second thing is that we have to maintain, it is a vacuum, right? We have to, we need to have a great vacuum there, so that no gas is left between core and, for example, this region, right? It's very easy to say, yeah, इसमें डाल दो यार और गरम करके निकालो, but in this region, this cladding tube and core rod, if you take this thing, in that boundary, there can be a lot of air gaps, and that can generate bubbles. Okay, and it can make you will get the fiber, but it will be very weak fiber. Okay, just making fiber is not important; it should be very strong. So that's why there are huge challenges with rigging to rodding tube method. And this can be avoided in chemical vapor deposition. It is straightforward method, chemical vapor deposition. Right, so we have 300, 500 degrees Celsius, okay. And we have SiH4, we have GH4, we pass oxygen, and we get SiO2, GO2, and other things. Go on adding these things. So it's very good. It's simple, not much temperature, very nice to take. When equipment was there, it was in. I worked in this equipment when I was there in Korea. Only thing with this method is that it is very painful. It's very painful to wait. So we have to keep it. That we take the slide SSL for. Sorry, we take SiO2 or some substrate. We keep the substrate, and then on the substrate we start the machine and flows, and we set everything on the computer machine, the flow rates, and at the end in the morning you will get 1 mm, 2 mm. So the thickness, it's very low thickness there. If you want more, then again we have to keep it there for 24 hours. Open it. If something happens in between, then it is spoiled. And another thing is water contamination. Right? So because we are passing different gases, and these gases are not really dry. We say gas, but it contains a lot of vapors there, water vapors. And if there is a water vapor, it will give huge OH related loss. Okay, that is generally, I will show you, I think there is some slide on that. OH is not good for our optical communication because it creates a loss at 1383 nanometer. But if there are huge OH content, that attenuation can go into 50-50 also. So we don't want OH, and there is a huge problem of OH here in chemical vapor deposition. Okay, but otherwise it's very simple. SH for dalo, GH for dalo, oxygen chodo, radbar rakh do, and you get that material. Okay, so to avoid these problems, what was done is that I'll skip this slide. Some, sorry, as I told you, it's growth speed is very low, few per day, and waste contamination problem is there. But there is one student who work on it in GIST, Korea, MTech student, MS guy. He work on that CVD machine, and yeah, he developed 2 thickness, that type of structure. Not for optical fiber, is a solid state structure for some sensing application. So it can still be used for sensing application. I think here, let's go for how it is manufactured. Okay, try to quickly show how it is done. It is simple method actually. It's very simple. Just, just make 300 degrees Celsius very easy to make, because if you got optical fiber manufacturing, that you temperature is huge, 2000 degrees Celsius, and compared to that, just 300 degrees Celsius, it is very easy to handle. So that is a good method, but it's not for optical fibers. If now we're going to MCVD process and all things. Professor, do we need to take break because, or shall we continue directly?
Sir, as per your convenience, sir.
If you guys need break, we can take. Otherwise, I will finish this.
We'll take 1 or 2 minute break and then we'll continue. 2-3 minutes.
Okay. Right. Let's have 5 minutes break. 5 minutes break. Yeah.
Yes, 5 minute break we'll take and then we'll continue.
Right. See you again, everybody, after 5 minutes.
Yes. So, dear participants, we have a break of 5 minutes. Sir will immediately join and we'll continue.
Right. Sure.
Yes. Welcome back, sir.
Yeah.
Yes, yes.
Yeah. I think everybody is joined, right?
Yes, sir. Well, please continue. Yes.
Okay, yeah, sure. Okay, welcome back everybody again. Is it okay to start right now? So,
Please, sir. Please.
okay, sure, sure. We'll see now modified chemical vapor deposition. As I told you last time, right? I will associate my experiences with this manufacturing and share with you to make talk a little bit interesting. Otherwise, it's just so there is some my memory associated with MCOD. I told you that I shared one memory that the Korean guys did not allow me to work on MCOD system because it was totally automated. So what happened one day? Uh, I was actually exhausted by making solution, and night time nobody was there. I went in the lab and started. Now we were trained right in IIT. We were trained like that. We used to repair it machines. So hardware, everything is known, it's same, similar, isn't it? So what we did is that at the time, I just bypassed that automated thing. We used to do manually, no? So and I make it semi-automatic. I mean, I use the flow rates from that one. Automatic. Uh, Other thing I didn't know actually. I was not trained to use them. So I just disable all those automatic things. We can see on the screen there were a lot of options. So disable all automatic things and started to use it manually as I was doing. That was the experience. And it was simple, right? I was able to make optical fiber in the morning till in the morning. I started maybe at 2 o'clock and till 6 or 7 o'clock, people started to come there. And yeah, they saw, oh, okay, this guy is making optical fiber preforms, I mean glasses, using MCOD, and he's not using any automated things. So our students in that group, our colleagues in that group, they were surprised. You are not using automated things. How can we make optical glass without those software controls? I told, yeah, we can make it. It's a basic thing, right? What do you need? We need to start the flows, give heat, and yeah, you can make we can make that glass. So really, then we became good friends after that. So that is the that's memory associated with it. Sometimes if you are trained at the basic things, you know, we can do anything in the world. Okay, we don't need any automated things. Just if you know the raw things, basic raw things, we can definitely go for that. So yeah, with that one, MCOD is a very good method. MCOD, I love this method. You can make any kind of fiber using MCOD. Okay, it is very nice. You can control it. You can do a lot of things with it. This was very simple. We have GSL4, SSCL4, focal, we say focal here, POCL, phosphorus, to increase index. GSL4 it gives UO2, that increases refractive index. SSCL4, that is the basic material. If we want to reduce the refractive index, we can dope it with fluorine or with fluorine or freon gas. Generally, we call it freon, or we can dope it with boron. So my main institute optical fibers work in Korea is generally boron dope optical fibers, and that was achieved using MCOD technique. So I used to put boron there, and when you put boron, the problem comes is that its melting point comes down. SSL4 means it will melt at around 1700 degrees Celsius to 2000, something in that range. And when you put boron, it comes down to maybe 600, 700. So huge, that thermal shock is there, and it can give rise to cracks. So to tackle that of things, only idea is to slow cooling. You can cool it very slowly. So everything good. It become very good. Okay, so it is very principle is very simple. You take you take what is called as tube, take silica tube. Or simple. We have SSL4, GSL4, POCl3. You can go on adding those bubblers. We call it as a bubbler because we send oxygen through it, and when oxygen comes out, it takes SiCl4 particles with it, and it goes inside. Here there is a burner. It is at 600, 1700 to 2300 degrees Celsius as per your design. So what we do is we are going to heat this burner. It moves from here to here, left, right, and we can fix this flow, that moving rate as per our convenience. We have to do a lot of experiments to fix that moving speed. So this is hot now. Okay. So we heat this glass tube. It's a ready-made glass tube. It's a silica glass tube. We take it, and through this we pass this chemical particle, oxygen containing SiCl4 particles, oxygen containing GSL4 particles, oxygen containing focal particles, or many other liquid you want to send there. So when, for example, generally if you are sending SiCl4 particles with oxygen, because of heat, the SiCl4 will come and plus oxygen, then you get SiO2. That powder is deposited here. So it's going here, so it is deposited here. And when you increase the temperature, that powder densifies to glass. It's very simple thing. Okay. Remaining SiCl4 and SiO2 that goes out, they go to the exhaust. So we have bath there, water bath, we call it water bath. So through it, this SiCl4 and they are collected there, they are removed. So it is very simple method, modified chemical deposition. Just we can make in your laboratory also. Just take glass tube. Only you have to ensure that there should be any leakage. That is the main thing. And we can pass SiCl4 particles. Okay. What actually we may not need these bubblers. The bubblers are very popular, but sometimes we can also blow these materials. Okay, by blower. A lot of things are possible there. It's not just this is a standard design, but we can play with it and try to send chemicals. Idea is to send some chemicals here. Okay, SiCl4 should convert into SiO2. So better to have SiCl4 particles, small droplets, very minute droplets, right? And oxygen, heat it, you get SiO2. You have GSL4 minute particles and heat it, and you can get GO2. So it is very simple thing there. Okay. So just pass these liquid particles through it, have oxygen, sufficient oxygen, so that they convert into oxide. So MCVD, modified chemical deposition, is a very good method, and it's very quick method because now we are not using 300 degrees Celsius. We are going for excuse me, 1 घंटे बाद फोन करता हूँ सर, 1 घंटे, 1 घंटे बाद करता हूँ. Sorry for that, you guys call me. Okay, so I was discussing it works at 1700, 2000 degrees Celsius, 2300 degrees Celsius, and we can in 4 hours we can make that 25 mm rod. That's what my experience. 25 mm rod can be made in 4 hours. So it's quite fast as compared to few mm in that that chemical vapor deposition. It took 1 mm, it took 24 hours. So that's the difference here. Yeah, so this is what MCVD is. It's very popular. It is not only for optical fibers. We can go for, specialty optical fibers. If you want to put erbium ions for amplifiers, ytterbium ions, so that can be done here. A lot of things are possible here. Even you can make photonic crystal fibers using MCVD. Just took different hollow tubes, club together and hit by burner. So that way it has huge applications. So it is very popular, modified chemical vapor deposition. But currently the industries, they don't use this MCVD. Some companies are using it, But if you are going for millions of kilometers, if you're looking at millions of kilometers in per annum, so in that case, MCVD, there are no use because there is a size, because the size of the tube, right? It is limited to 25 or 30, 40 mm diameter. And we are looking for 200 mm, something bigger diameters, so that we can make or manufacture more and more fibers to cater our customers. So in that case, right, yeah, if you're millions of kilometers, you're looking for that MCVD, surely it's no use to use this MCVD method. But for specialty fibers, for if you are looking for not 50 million fiber kilometer a year, not that way, okay, not in that range. If you are happy with 25 30 mm dia, preforms, then we can use MCVD. So it is still used by many companies. And I'm always using freeform, right? Freeform. What is freeform? Freeform is you have tube here, and we are depositing SiO2 or GO2 in the inner coating or inner surface. On this inner surface, we are depositing SiO2 and GO2 or phosphorus, whatever you want. And this is the deposited layer. So, and inside there is a gap. So what happens that now we increase the temperature to 2300 or 2000 degrees Celsius, sometimes to make it fast 2300 degrees Celsius. And this is moved from here to here. So what happens slowly, this dia start to reduce. And finally, the guys stick together. These two layers stick together and there is no gap at all. And so we get a rod, full rod. This was earlier it was cylinder. Right, then we drop the regions here, and now it is a rod. So that rod is called as preform. Okay, preform is nothing but a glass rod without any central gap. It is a glass rod. In any rod, glass rod is preform. We call it preform. So preform means glass rod. Okay. Otherwise, if it is a tube, tube means tube. There is a inside there is a gap. That is a tube. So to make the preform of 25 millimeter dia, 30 millimeter dia, we can use this MCVD. And if you are going for 100 kilometer at a time, in one go, 100 kilometer, 200, we can use MCVD. If you are going for 2000 kilometers in one go, then we cannot use MCVD. We have to use other method, that is OVD. I will see that OVD and VAD. Okay, I think this is the MCVD. It is how it looks like. It's a very simple thing. It is an optical lathe. This is the glass cylinder here, right? And this is going because of this is the burner. This is hitting this tube. Inside there is you can see the white region, right? White region means there is a SiO2 or GO2 layers are formed, and we pass maybe from left side. We are passing our, I think from this side, it's close here. From this side, we are passing our gases and the SiO2 GO2 is formed here. The Hathway system in South Korea. So let's see how this MCVD system works.
All of our preforms are made on site according to a fiber specifications. This is Bill Tweedy. He kind of runs the place. How are you, Bill?
Good, how are you?
Why don't you tell us both what kind of happens right here in this lab?
Well, basically what we do here is the MCVD process. We make core rods that are then used in this sleeving process to make larger preforms that they draw into fiber. We could do anything in here from PMs to rare earth doped fibers on a consistent scale and on a very large or a very small scale.
So he is telling that we can make any fiber structure here. Okay, rare earth dope for amplifiers, as well as polarization maintaining fibers, photonic crystal fibers. Many structures can be made using MCVD.
Depending on what the customer needs.
Oh, thanks, Bill. Appreciate your help. So that's the first step in the process. Any questions? No?
I hope you also don't have any questions. So that's how MCVD is very popular. But if you are going for mass production, you have to look out for other methods, because MCVD can give in 200 kilometers, not in thousands. So these are control systems. We need not go through it. All right. So other method then is there are two other methods to accelerate the optical fiber production. Idea is same. You have chemicals. You make preforms. Now to make bigger preforms, not 25 mm diameter, but 200 mm diameter, 100 mm diameter, 200 mm, 150 mm diameters. Such bigger size preforms. We need to go for axial deposition, and there is outside vapor deposition. The two methods. We'll see one by one. In axial, what they do is that we form SiO2 and GO2, and simultaneously. So what they do is that the SiO2 plus GO2 from it is at the axial point. We using the burner, we deposit SiO2 plus GO2. At the same time, SiO2 is formed. Okay, how that is done, I will show you. See here, as you can see, there are two burners, right? So this is the inner burner, which is SiO2 plus GO2 is from here, and it is surrounded by this is SiO2. Okay, so we find SiCl4 here, oxygen plus SiCl4. Here, oxygen plus SiCl4 plus GCl4. So they form the core region. This form the cladding region, surrounding region. So at a time, this thing happens. This is called a soot. Okay, so once you deposit this thing, so we get this bigger soot. Now you can see, you cannot imagine that type of dimension using MCVD. Okay, that is 25 mm. Now this dimension may be 100 mm or maybe 150 mm. It's bigger, very big size. You can draw 2,000, 3,000, 4,000 kilometers in one go. So that's what we have seen, how axial deposition is done. In axial deposition, what we do is that at the center we deposit GO2, SiO2, and at the same simultaneously we deposit SiO2 as a cladding over it. So it is it can manufacture very big size preform, 300, 400 mm, and we can get a lot of fiber at time. Yes. Only problem is that now something happens there, right? Some bad thing happen because the SiO2, GO2, the shape is not correct or something happens. Then that huge lot of soot you saw that, right? Bigger soot, that you have to throw it out. So huge loss there. So if there is loss, there is a huge advantage is that we can make a lot of fiber using OVD, sorry, using axial deposition. Then to take care of that, we have another method, that is outside vapor deposition. So how to do that? It is again SiO2 GO2 there, right? Only thing is that now we do in steps. Okay, so if first we make core SiO2 GO2, then we make over it. In the second stage, we make the cladding. Okay, so something, and we can make any dimension as we need as per your machine. What is the advantage is that if you make the core, right, something bad there, so we have to throw it out. Only core is thrown out, so we don't need to throw out the whole whole preform or whole that big deposited material. We don't have to throw out. So that's the advantage. So, that's why companies are using OVD. Yeah, but people are using VAD also, because advantage is it can produce more kilometers of fibers as compared to OVD, and it is a one-step process, so it is very fast. In axial deposition, we have core plus clad at a time. In OVD, we make first core, SiO2 GO2 is deposited first. We make the glass out of it, and then we take that glass again deposit SiO2 over it, that form the cladding. So it is a two-step method. So time needed is more. This I will explain it here how it looks like. So we have this target rod. So generally we take graphite rod. Some companies use glass rod, but it can be brittle. So we take the graphite rod here. It is very strong. And over this now we deposit some layer, right? We have burner here and we deposit the soot. We don't get glass it now. We deposit the soot, white colored soot. I'll show you the picture. So we keep the temperature lower so that the soot is deposited here. So that's the first stage. Then we put this into the furnace. Okay, if we put this in the furnace, we increase the temperature to suppose 15 degrees Celsius, and this is now the soot gets converted into glass. So we get the clear glass rod from soot to clear glass rod. Then again we take that glass rod and deposit SiO2. Again we get the similar structure. If you furnace mein, you get the clear glass, and then we can put it in the drawing tower and draw the fiber. So it's a complex structure. I will show it here how it is done one by one. So we have target rod here, and over it we deposit. We see we are sending SiCl4 and GaCl4 to the burners. There is oxygen and hydrogen for gases as well as reaction. This is the heating here. The burner, two burners here. We also have three burners. So what happens? SiCl4 and GaCl4 converts into SiO2 GO2. Okay, but we keep temperature lower so that we get soot here. So this is the soot. You can see at right side. It is a white colored soot. Okay, its diameter is maybe 125 mm diameter. It's a bigger, very big size, and 1 meter height. So we get such type of soot. It's called it soot. Okay, I think it is clear, right, everybody? We deposit SiO2, GO2 in the small particle format. So we get the soot here. It's the first stage. And yeah, once we have these things, we put it in the furnace, and that furnace converts this into hot furnace at 1550 degrees Celsius. The soot gets converted to glass, means it's a clear glass. Okay, that is. Let's see how it looks like here. So as you can see, right, its diameter is getting increased because we are continuously depositing SiO2 and GO2 particles. So it's a soot, and it takes around 12 hours, 10 to 12 hours to get 100 mm dia. So we take that soot and put into the furnace, so that we convert this soot into the clear glass. Yes, it is. So we get the clear glass. Earlier it was soot, right? Opaque soot. Now it is clear glass. So that's how we make the. We call it as a core rod. Now we take this core rod, Over this, we deposit another SiO2 region, SiO2 layers, these particles. So another soot is formed, again put in furnace, and we get the final structure, which is glass, which has now 2 layers. Inside there is core, SiO2, outside there is SiO2. We're not going to much detail of sintering. It is just furnace. We put it there. So very simple thing here. Sintering. How do we take? This is the other picture from Sterlite's manufacturing plant. This is our soot, right? We take it and put in the sintering process. This is very big furnace here, 2 meter long. Height is very high. And finally, from this soot gets converted into such as transparent rod. Okay, and the shape is a little bit deformed, you can see, right? Because it's high weight process. There is a gravitation pull, so we can get a little bit higher width here. So that's a common thing there, but we have to adjust during drawing all things. So this is called a sintering. You take a soot, put it in the furnace, you get the glass, that is sintering. So we finally get a sintered preform. And we also need to do degasification, because what happens is that we always use helium. This is a soot, right? Soot is going to be converted into glass. There is a huge possibility that some gas is trapped inside. This soot, right? This soot means there are a lot of pores are there. So if some gas is trapped and you consolidate it to glass, what happens that because of high temperature, that trapped gas can expand and form the bubble that can break your fiber and break your preform, or nothing happens, then it will make your fiber very thin. Very weak, so nothing. So that's the disadvantage. So we have to be very careful that the pores are not there, so that the bubbles can be avoided. To do that, what we do that we send helium. Helium has beautiful property that if it sits in the pores, and when it is heated, it diffuses out quickly, and we get very clear preform like that way. And yeah, I know now we are giving gases there, so we need to take out all those gases. So to suppose trap gas, there are some trap gases. To get them out, we need to give it sufficient time. So we have our own method. Every company has its own method. So we keep it for 18 hours. We just take that preform, keep it there in one box for 18 hours. And the helium naturally diffuses out. If something is there, it will diffuse out. Okay, that is called as degasification. So I think you don't have much time here. Okay, gasification of porous glass to coarse. So this is our porous glass soot. We need to get this clear preform. To do that, I'll just show some pictures. As I told you, right, there are pores. So if you take this region, if you take this region, what happens is that when we have soot, it looks like this way. Okay, so there are a lot of pores here. So gas is trapped here. It's very necessary to remove any gas trapped in this pores. This is the microscopic structure of the soot. So, and as you go on heating, these pores are reducing, isn't it? Slowly, all pores are reducing, and finally you get this clear glass. Okay? So that is the simple process here that is proved by these pictures. I think I should not discuss this helium argon, but just for your what generally we use that we put helium and argon gas to remove those pores. Okay, so 100% helium, your bubble free is completely bubble free, but helium is very expensive. So what we do is we add some argon there, air. Okay, if you add argon, there is a lot of possibility that bubbles can be formed. Okay, so optimum ratio is very important. 60% helium is the optimum point where we can get bubble-free glass. Now this can change. This ratio can change. Okay, your depends upon your glass. So depending on company to company, their material, their manufacturability, their manufacturing process. So this ratio can change. But generally, 50-50, 60% helium is needed. Okay, so why it is so? This reason is that. Okay. Generally, our pores are smaller in size, right? Generally, 1 micron size. Pores that we saw, they are 1 micron size near less than that. Some computers are 2 microns, some are 10. So there are different sizes of pores are there. Now, if you have helium, what is? I will show you what is called as. It is called as critical dia. There is a critical pore size. Okay. So if your pore diameter is less than critical, then it shrinks. If your pore diameter is more than critical, then instead of shrinking, it expands. Madam, can you mute your mic, please? Okay.
Nivedita ma'am, please unmute yourself. Sir, please continue.
Okay, right, sure. Sorry for the disruption. All right, so what I want to convey, we don't need to go into much details of the helium or argon. What I'm saying is that we generally use helium and argon gas, okay, to remove these bubbles. Okay, so that optimum ratio is very important, helium and argon. The reason is that the critical diameter for helium is 500 micron, and while in argon it is just much lower than that. And so there is a lot of possibility of having bubbles with argon gas than compared to helium, because as you can see, right, critical pore size of helium is 500 micron. Critical pore size of argon is 0.6 micron. If your pore size is suppose 1 micron, it is more than this air, right? So it will form the bubble if you are using argon. If you have 1 micron pore size, it is much less than this critical. So it will not expand, but instead of that, helium will diffuse out. So that's how we manage these bubble things. But still, even though you are using these optimum conditions, still bubbles can form. There are many reasons. It's not so simple. Okay, skip this thing, helium to this. Other ways to reduce bubbles is that we generally keep difference, along the time. The difference in temperature is made as small as possible. I mean, we slowly cool it. Okay, so slow cooling is the key for bubble-free preforms. Now scoop this thing. All right. Now we understood that how to make preform. Right. I hope there is no confusion with it. We make soot. We make glass from that. That is GO2 SiO2 that forms the core. Over that glass, again we form another soot. Again we sinter it to glass. In this way, we make the preform. Now, once your preform is ready, what we do, we take it, and now it is ready to draw the fiber. It is a simple process now. We take preform, put it into the graphite furnace, okay, heat and increase the temperature to suppose 2000 degrees Celsius. Okay, now what happens when you heat at the tip of this preform is glass rod. Okay, so it will melt down. This heat tip will melt down, and because of gravitation comes down. That part. We catch it. We manually catch it actually. We catch it and then manually pull it down. So खींचते हैं नीचे. And there are wheels here. Okay. So this is continuously rotating. So we put here and And as it is rotating, it start to pull it continuously. Okay, so every form is hitting continuously, it is coming down, and it is here, it is pulled automatically afterwards. Initially, it is manual. We put it here, that fiber. Okay, that fiber we put it here, and then because of these rotations, this start continue pulling the fiber. Now this only this glass fiber is no use. We must coat it with plastic, right? So what for that purpose we use DSM monomer. DSM monomer is used. So this is it is here coating applicator. Okay, so we put monomer here. That is just very complex formula. Like DSM has a patented complex formula, plastic formula. You are from anybody from chemical engineering. So this monomer is here, and when this fiber, this glass fiber passes through it, now it is get coated with that monomer. Okay, and then when it comes here, it is a UV ultraviolet rays are kept here in this furnace. So when it passes through this UV chamber, because of UV, that monomer converts into polymer. Okay, and we get the plastic. That is the coating over the glass rod, and we get the optical fiber here. We collect it here in the spool. Okay, 200 meter per meter. So what is customer requirement? We keep the spool like that. Okay, so this is the way to manufacture optical fiber, to draw the optical fiber. This is not available here. Okay. So this is how drawing tower looks like. It's a big 5 meter, 10 meter drawing towers. We can have furnace here, you can see, right? A lot of controls are needed. It's very simple to show on the diagram, but there are many controls. It is just 125 micron. This fiber that is coming through this glass. So we have to adjust it for 125 micron dia. So that much accuracy. And then it is coated with polymer. Its dia becomes 250 micrometers. So 125 becomes 250. Okay, if you take coating plus glass fibers, but glass is only 125 micron. In that glass, there is a core which is only 10 micron. So those are the dimensions. 10 micron over 125 micron dia. Then over that there is plastic, which is if you take total, it is 250 micron total dia. This is the drawing tower. It is shown here how this fiber comes out, right? This is the furnace. So the furnace, this fiber is coming out. This is a narrow line here. Okay. This is the way. This is our preform. Now this is the furnace here. So it is inserted into the furnace. It looks like that. And yeah, finally, so we draw what we get. We call it as a fiber. So now fiber has inside core. हमने core डाला था GO2 SiO2 surrounded by cladding and surrounded by coating now, polymer coating here. This is called as optical fiber. This inside this is 125 micron, and outside if you dia is 250 micron. These are the standards, IETE standards. Okay, International Telecom Union is our union here. So these standards are followed. IEEE, but IETE, they are convergent. We follow those standards, and finally is 150 micron fiber is ready. Okay. So it has refractoriness like this way. This is your cladding. This is the core. Inside there is deep. This is very common. Deep. I will expect some question why there is deep. In MCVD, generally, what happens is why there is deep. The reason is that we are putting germanium dioxide and silicon dioxide, right? SiO2 in the core. This is the core region. And when we are hitting, what happens that GeO2, some part of GeO2 becomes GeO. Okay? GeO2 is solid, GeO is gas, so it comes out. And germanium dioxide gives the higher refractive index. So as germanium is gone, you get lower refractive index, and so we get the dip. That is the reason for dip inside the optical fiber. Okay? We don't get this dip if you are using vapor axial deposition. Okay. In OVD, we also get deep, even though there is no GeO formation, we get deep. The reason is that in OVD, if you remember, we take the target rod, a graphite rod, over which we deposit, because we need something over which we have to deposit, right? So, and we have to remove that target rod. So while removing, we actually damage it a little bit, and so we get central dip in OVD also. So OVD has central dip, MCVD has central dip, axial deposition has no central dip. Okay, now fiber is ready, then we have to go for D2 soaking. If there are any questions, you can ask me, or you can write down. We can discuss at the end, because we are coming to the end now. Why D2 soaking? Deuterium, right? This is used in atomic applications. Deuterium. We need that D2. So understand why we need D2. Just drawing the fiber is not enough. Now it has to pass through various tests. So one of that is D2 testing. D2 soaking. Why we do D2 soaking? As just for introduction, here we have amorphous structure, right? These molecules are loosely bound. There is no great structure. If the crystalline structure, it has very nice structure there. Okay, amorphous can become crystalline if you give enough cooling time. Okay, naturally, if you give enough time, this amorphous can become crystalline. In case of glasses, this amorphous glass can become crystalline glass if we keep it cooling slowly in such a rate that this amorphous can become crystalline if you keep it for slow cooling for about 1000 years. So keep it, okay, take amorphous glass, cool down it slowly, keep it for 1000 years, you can get crystalline glass. Wait, right, that's the way to get amorphous to crystalline. Okay, so it has SI. We always say SI has 4 bonds. One is towards you. That's how we show. Oxygen has 2 bonds. This is crystalline structure. This is amorphous structure. And when you put hydrogen there, what happens is that, see, this is SiO2, right? SiO2. So SiOO, and there is covalent bonding. So there is OO structure here, OO here. If hydrogen comes, what happens is it removes this. It forms H plus OH here. Okay, it can attach to oxygen, and that bond is broken. I will show you how it is there. So how it looks like. So you have SiO2 structure. How it looks like? This is in the glass. This chain, the amorphous chain, is Si. It has OOOO, right? Si, this is O. This O is common. So Si O4, or O. This O is shared between another Si. This O is shared between another Si. So it is SiO2 actually. So this oxygen between Si and this Si, this is called as bridging oxygen. So bridging oxygen. It's a bridge between 2 Si atoms, right? It is shared by 2 Si atoms, this O. And now you take it out. If you take out that bond, now Si is left with O. O has nothing. There's no bonding with Si. This is called as non-bridging oxygen. So in glasses, we have a lot of non-bridging oxygen. Okay, it's very faulty structure. So even though it's amorphous, the bonds are not correct. There's a lot of breakage of bonds. So many non-bridging oxygens are available in the glass itself. Okay. Now if you keep it is like that, what happens? The hydrogen can come and attach with this, right? Hydrogen can come and attach with this. So it becomes OH. OH gives a huge attenuation at 1383 nanometer. Okay, so there is a huge attenuation because of OH in glasses. Okay, so because how to avoid that, hydrogen is always there, right? Because we have polymers coating that is made of hydrogen. There's a lot of hydrogen there. It can diffuse out, diffuse in. Environment has hydrogen. If you keep it for many years, 10 years, 5 years, so the hydrogen can enter there. And if hydrogen enters there, there will be huge loss, attenuation, and your network will fail because of that attenuation. Then how to avoid that? How to avoid these things that is not matter right now, but in future it is going to fail our fiber. All system will collapse because of this hydrogen diffusion in the fiber. So what we do then to avoid this futuristic problem, instead of we put deuterium here, D, right? D is same as hydrogen. So if you put D makes bond with O. Now we have OD, not OH, OD. This also creates attenuation. It's not that it is free of attenuation. This also creates a loss in the optical fiber, but that loss in very high wavelength region, that is 1.9 micron. We don't use that region right now for communication. Whenever we use, then that will be problem there, right? Right now we don't have that problem. We use 1.55 micron. We use 1.3 micron. That type of bands. If you put D there, we are going to get attenuation 1.9 micron, the higher wala band. If you add H there, OH, it will give attenuation 1.38 nanometer. So 1.3, हमारी useful band है. 1.30 is very near to it. So OH is very bad for communication. So if you replace, the non-bridging oxygen, this bond is made with deuterium, then OH, all these empty spaces are filled up. Oxygen, hydrogen, if hydrogen enters there, it will definitely enter hydrogen, but it has no place to bond with. Oxygen all occupied by deuterium, and deuterium makes attenuation in 1.9 micron, not in 1.55 or 1.3. So it won't affect our communication, optical communication. So this way we can avoid the problem of OH attenuation, okay, in future because of hydrogen. Right, so high attenuation at 19009, that I told you, deuterium makes it way. So we can avoid OH attenuation in future by adding deuterium at the manufacturing of optical fibers. So once we manufacture optical fibers, that's what we do. We take it and put it in the chamber containing deuterium. Just only 2% deuterium. That's all. Keep it for 18 hours at room temperature, and it's okay. It's good to go. All right, so I will just keep it here. Then once you now made the optical fiber, we soak it. We do the coloring. Sorry, we do the cabling. Now, before doing cabling, what we need to do is that we need to color it, because there are many fibers, right? There are thousands of fibers. So cables I have many fibers, not just one or two fibers. It can have thousands of fibers. So we need to color the fibers. We need to group them and color them. Okay. So we group them, we take the fiber, color them. Okay, suppose 8 fibers, you have 8 colors. Then we put it in one bunch. It's called as buffer. It's called as buffering. Or एक rod डालते हैं उसमें, inside we put that fibers. It's buffering. Then we use jacketing, means outer cover, and we get the finished good. So how it looks, I will show you. So this is your typical cable. There are the fibers here, right? This is jelly filled here, and this is the another tube. We call it a Goose Tube, plastic tube. This tube should not come in contact with fiber, so we add the jelly here. Some oil-like structure, jelly, between fibers and this loose tube, or this tube, plastic tube. And all these tubes are now contained in the bigger tube. That's a very big, big tube. So that if even the truck is going over this one, nothing should happen to your optical fiber. We have to deep it, bury it underground. So like that. So we have to make it very strong structure. So this is the called as cabling. In cabling, we take optical fibers. We can see many optical fibers here. It has different colors. Then we have loose tubes here with different colors. So that way we have to distinguish. We can distinguish optical fibers. And at the center, as you can see, there is we keep it very strong material there, so that these tubes should not collapse on each other. Okay? We can take a central strength, we generally call it central strength element. It is fiber reinforced material. It is very strong material, so that these guys should not collapse on each other. So this is the structure of optical fiber cable. And we do a lot of testing there. Okay, it shows 24 fiber, gel field, tensile strength, a lot of things has to be done there, and it has to protect from rodents, mice, right? These mice that can damage the cable, so we have to put that type of insect resistance nylon jacket, okay, and add some chemicals so that this mouse should not like it. This test. Okay, so we put some chemicals. That taste is not liked by mice, and we can save our cable. That is our cable. Let's keep this state. Okay, and so that's all. Yeah, how, so we studied from how we may choose the material, how to make fibers, we use different techniques, and then after that we draw the fiber, then we put put coating over it, then put into the cable. We use different tubes. The tubes are again contained in the bigger tube, and to get the cable. This is how optical fiber is manufactured. Thank you very much. If you have any questions, I hope that you enjoyed this brief introduction to manufacture optical fibers. I tried to share what I know as per my experience. Now this discussion is open for queries and talk.
Thank you, sir. Thank you very much. Dear participants, the session is open for discussion now. I request also to raise their hands to ask the question to sir. Sir has delivered a very nice lecture on this optical fiber manufacturers from
Yeah, I cannot hear, right? Any question? Yeah. Yeah, sir, I cannot hear. Yeah, okay now. Again go on. Right, now it's okay.
Mayur, please ask your question. Mr. Mayur, unmute yourself and ask your question. Then next is a Piyush Vishwakarma. प्रमोद सर माझा आवाज येतोय का?
हो हो.
हां.
आधी नव्हता आला.
हां. ते अनम्यूट करायचं राहून गेलं. मयूर प्लीज. हां बोला.
Yes. First of all, thank you for the very good, very nice seminar, sir.
Okay, thanks.
We have explained a lot of things which are very basic, means which are core. No one will explain that much. Thank you for that. Currently, I am working as a PhD student in the International School of Photonics, and I am working. My PhD topic is polymer optical fiber-based waveguide devices.
Okay.
So you have not explained anything into the polymer, but I would like to ask some questions. That are you preparing the microstructure polymer fibers, something like that?
Actually, Mayur, thanks for your question. We are not working with on polymer optical fibers in Sterlite. The reason is that it has a huge attenuation there. So when we are manufacturing commercially, there are standards given by ITUT. So we have to follow those standards, and making polymer optical fibers and follow those standards is very difficult. I mean, commercially, it's not viable. So we are not going for that. So I have not touched that topic. But yeah. Now the research Chinese groups, they are always going for PCF size structure. We can always go for short distance, short length, photonic crystal fibers using polymer. So there are many good research are available there. Unfortunately, I have not worked on that in that field. Yes. So there is no plan. As to answer your question, in Sterlite we have no plan to manufacture polymer-based fibers. We tried actually earlier. It was rejected because of business sense, right?
I asked about microstructure polymer, microstructure fibers, which might be silica also. Are you preparing?
Yes. Okay. We are actually this year we are going for microstructure optical fiber. Yeah, we call it photonic crystal fibers.
Yeah.
Right.
Actually,
So we have the plan.
I'm also looking for doing research into that field. So
Nice, nice.
I would like to visit your company whenever I will in that.
Right. You can always visit it. Just write to me, and then we can arrange your visit here. You can
Thank
take
you,
the
sir.
facility. Right now, we are in the initial stage, or design stage of photonic crystal fiber.
Yes, sir.
So we're design and then manufacturing. We are planning to have collaboration with CGCRI,
Okay.
Kolkata, because all our MCVD systems they are now converted to for our rod joining systems. We don't use MCVD anymore because the type of structure needs MCVD, modified chemical deposition. But yeah, we'll procure it. Meanwhile, we're planning for collaboration with IIT Delhi and then with CGCRI. CGCRI have good facility there, manufacturing facility. Then we'll establish facility here also. So right now we are in design stage.
Thank you, sir. Really, thank you.
Yeah, sure. Thanks.
Next is Mr. Piyush. Dr. Piyush, unmute yourself. Dr. Piyush Vishwakarma, unmute yourself and ask your question. I think he is unable to unmute. Anybody next? If anyone is having question, they can raise their hands. Sir is ready to answer.
Yeah, if you have queries, we are still there meeting tomorrow also, right?
Yes. They can ask tomorrow also.
Yeah,
Yes,
right,
sir,
that's
yes,
fine.
sure. Now I request my colleague Dr. Swapnil Undalkar sir to propose vote of thanks.
Thank you, sir. Presentation that have the goal of increasing others' knowledge, understanding or abilities, then yes, it is acceptable. Good evening to all. It gives me an immense pleasure to have been asked to extend a vote of thanks for this session. First and foremost, I would like to thank eminent distinguished resource person, Dr. Pramod Watekar sir, Sterlite Technology Limited, Aurangabad, for his informative session. Sir, by attending your session, I can say if something is having novel properties, then we must take into account. Thank you, sir. We are extremely thankful to our HOD coordinator of FDP, Dr. Abhijit Yadav sir, for organizing such an extraordinary faculty development program on photonics. Thank you, sir. I'm very happy to extend my sincere thanks to all delegates, HOD, faculty members, research scholars, students for accepting our invitations, registering, attending, and your cooperation in making this session, this day, a resounding success. Last but not least, I would like to thank all the members of organizing committee, Dr. D. V. Rajesh sir, Mr. M.B. Kumbar sir, Atul More sir, Vijay Zadke sir, and Mungle sir, and all good hearts who worked behind the screen. Unless you try to do something beyond what you have already mastered, you will never grow. And this FDP is organized to enhance your knowledge in various fields. And this concludes vote of thanks. Thank you. Over to you, Yadav sir.
Thank you, sir. खूप छान झालं. छान.
Thank you very much, and thanks to participants for attending class.
Tomorrow.
Thank you, sir.
Thank you. See you tomorrow again.
Yes, sir. Yes, sir. Thank you, sir. Thank you very much.
Thanks. Bye-bye.
Dear participants, this ends day first of this online faculty development program on photonics. Up to 7 p.m. you will get a link for the quiz, daily assignment, as well as link for the feedback. Do complete that quiz as mentioned in the WhatsApp group. Also, tomorrow we have a very renowned professor, Professor Dr. Ajay Ghatak, who will be talking about what is the quantum theory of light. And he will be delivering his lecture at 10 a.m. in the morning. So all are requested to. आवाज येतो कुंभार सर माझा?
हाँ ये तो
Yes,
सर
sir.
ये तो है.
All are requested to join at 10 in the morning. Please join before 5 to 10 minutes. Thank you one and all. Thank you.